Hi, I am Heidi Tricia Santos from BS Math 2A, and for this video we will be answering one problem regarding surface integrals. But before we proceed with the actual problem, let's discuss briefly the surface integrals. So let's start. So the definition of surface integral is a definite integral taken over a surface S in three-dimensional space. Here is the sketch of some surface S. In this case, region S will lie above some region D that lies in the xy plane. We use a rectangle here, but it doesn't have to be, of course. Also note that we could just as easily look at the surface S that was in front of some region D in the yz plane or the xz plane. Now, how we evaluate the surface integral will depend upon how the surface is given to us. There are essentially two separate methods here, although as we will see, they are really the same. So here is the first method or formula. So we have the double integral of f of x, y, z, ds over the region S is equal to the double integral of f of x, y, g of x, y times the square root of the partial derivative of g with respect to x squared plus partial derivative of g with respect to y squared plus 1 dA over the region D. Take note that this formula can be modified depending on the given D region. Now, here is the second method that we can use in evaluating a surface integral, especially when the surface is given by the parameterization. So we have the double integral of f of x, y, z, ds over the region S is equal to the double integral of f of vector r of u, v times the magnitude of the cross product dA over the region D. So to better understand the concept of surface integral, let's try to answer one problem. So evaluate the double integral of x plus y squared plus z squared ds over the region S, where S is the portion of x equals 4 minus y squared minus z squared that lies in front of x equals negative 2. To formally start our solution, let's write down the given notation. Now, we'll proceed with visualizing the region S through a 3D graph. So, the violet region represents x equals 4 minus y squared minus z squared, while the red plane represents x equals negative 2. Note that the surface in this problem is only this elliptic paraboloid and does not include the cup at x equals negative 2. So we are only concerned of what lies in front of x equals negative 2. At this point, it should be clear that the surface is in the form of x equals g of yz equals 4 minus y squared minus z squared. Therefore, the D region is in the yz plane. To get D, we just need to equate the two equations, and here is the process. So our D in this problem will be the circle y squared plus z squared equals 6. Now, among the two introduced methods a while ago, we can use the first formula with a little modification here. Since everything is settled, let's go back to our solution. Let's just use our formula and plug in our values. Notice that we have also plugged in the equation of the surface x in the integrand and input the partial differential of g in terms of y, which is negative 2y, and the partial differential of g in terms of z, which is negative 2z. So let's just further simplify this before proceeding with the actual integration. Now, for this problem, it should be clear that we'll be using polar coordinates to do the integral. Since our D region is a circle or disc, we'll use the following limits. We have theta will be the limits from 0 to 2 pi, and r will be the limits from 0 to square root of 6. Now that our limits have been settled, let's set up again our integral with these limits in polar coordinates. Again, In evaluating double integral, we must start to integrate with the innermost part. However, notice that we can just easily integrate this, so we will be needing to undergo integration by substitution. And here is the process. By using the result obtained from the u substitution, we have the double integral of 4 square root of u times du over 8 d theta, evaluating from 0 to square root of 6 and 0 to 2 pi. So 4 divided by 8, we will be left with 1/2. Since it is a constant, we can place it outside. Now, the integral of square root of u, or u raised to 1/2, is u raised to 3 over 2 over 3 over 2. So, let's further simplify this before we proceed with the evaluation part. Now that it has been settled, let's evaluate this from 0 to square root of 6. So, let's replace r with square root of 6. After the minus sign, let's replace r with 0. Again, let's do some basic algebra and simplification. So we arrive at having the definite integral of 124 over 3 d theta evaluated from 0 to 2 pi. So the integral of this constant is just 124 over 3 theta. Now, we will evaluate this from 0 to 2 pi. So let's replace theta with 2 pi. After the minus sign, let's replace theta with 0. So again, let's further simplify this. And there you go. The answer to the given surface integral is 248 pi over 3. So that's all for this video. Have a nice day ahead.